Hello, welcome. In this video, we are going to prove that for Q not being equal to 1, we are required to use the principles of mathematical induction to prove that the sum of this series A plus AQ square up until AQ to the n minus 1 is equal to A 1 minus Q to the n over 1 minus Q. Now, this is how induction works. It's more like a ladder to climb something. So given a ladder to climb something, we start with a base case, which is the case of n equals to 1. And then you establish that if n is equals to 1, then n is true. If n equals to 1 is true, then it means that n equals to 2 is true as well. So you have two things to do. You have to prove that n equals to 1 is true, and you have to also prove that if n equals to 1, then that means that n equals to 2 is true. And also, if n equals to 2 is true, then this means that n equals to 3 must be true as well. Now, if you can establish that whenever n is true, like whenever n is true, then this means that n plus 1 must be true. If you can establish this notion, which is the backbone, I'll call it the backbone of induction. The backbone of induction. If you can establish that whenever n is true, that n plus 1 would be true as well, then this tells us that this statement will be true for all values of n, because whenever it is true for 1, it is true for 2, true for 3, true for. But first of all, before we begin to prove that whenever it is true for n, it must be true for n plus 1, we must prove that it is true for one small case, which is the base case. So either we start with n equals to 1, or we start with n equals to 2, or n equals to 3, or whatever case we start with. If we start with n equals to 7, for instance, you can start with n equals to 7. But if you start with n equals to 7, you must have to prove that it is true for n equals to 6, it is true for n equals to 5, and also n equals to 4. If you decide to skip all these n's and start with n equals to 7, because if you prove that if n equals to 7 is true, that implies that n equals to 8 is true. If you could prove this will be fine. But you only prove to us that from n equals to 7 going down, the statement is all true. That is what you prove to us. But we don't know the part of n equals to 1 to 6. So mostly the base case begins with the case n equals to 1. So let's look at this case now. We first of all establish the base case. So the base case, suppose n equals to 1. This formula to be true for n equals to 1. Now, this formula tells us that if we sum from this series A to n minus 1, we should get this. So when n equals to 1, this is the n term. The series becomes n minus 1 is 0. So this is AQ to the 0th power, which is A. But when n equals to 1, which is the formula, we'll have 1 minus Q to the 0th power. No, sorry, not 0, but Q to the 1 power, all divided by 1 minus Q. So we can always cancel out the 1 minus Q, since Q is not equal to 1. So there's no danger of dividing by 0. So we get an A. So both sides agree. So the equation A agree with the equation, like the base case has been established, because for n equals to 1, this whole expression and this whole expression are equal. You can always start. Mostly people feel like because it's easy, like the case n equals to 1 is very easy, so it should not be correct, or it should be, it's too cheap. Now why not n equals to 3? But the thing is that simplicity is the best. Start with the simplest case. No matter how easy it may seem, simplicity is always the best. So we should always not disregard simplicity just because it is easy, just because we got it so fast does not mean that it's cheap. Actually, this simplicity is the best. So let's see the case when n equals to 2. The case when n equals to 2, we don't have to, but just examine the case. That would be A plus AQ, because n equals to 2 means that we should stop at 2 minus 1, which is AQ. So we are going to sum A plus AQ. Now, what about, does it equal A 1 minus Q to the 2nd power over 1 minus Q? Well, it equals actually, because if you notice that this is equals to A 1 minus Q multiplied by 1 plus Q, and then we're dividing by 1 minus Q. When these guys cancel out, A multiplied by this will be A plus AQ. So they actually equal. And the case where n equals to 2 has also been established. No, we don't really need to establish this case because just the base case is sufficient for us. Now, what about the case? How do we now prove the result in general? Let me take this off. Oops. Well, to prove the result in general, what we need to do is to assume it is true for some k or for some n. So let's see, give me some seconds. Let me take off this part. All right, so let's say to prove the result. Now, we have shown that at least the base case on the base level is true. Now, assume that it is also true for some particular n. Let's say we know it's true for n equals to 1. We know it's true for n equals to 2. Now, assume that it will be true for some particular n. We want to show that it will also be true for the next n flowing it. That is what we want to show. If it is true for one n, it should also be true for the next n on the ladder. This is the closest n, it should be true for it. Now, we assume that the statement, the formula is true for n equals to k. Like n equals to k. Let's say this case we have proved it's true for n equals to 1 and 2. Well, assuming it's true for one n equals to k. This means that a plus aq plus aq squared plus up onto aq to the k minus 1 is equals to a 1 minus q to the k over 1 minus q. Now, this is the formula for this formula, we assume it is correct for k term. The k, you don't need to ask yourself, what is k? What k is that? No, we just say, okay, since it's true for n equals to 1 and n equals to 2, let it be true for some particular value of k. All right. Now, the next task is that what about for k plus 1? What about k plus 1 term? Well, let's calculate k plus 1. Well, that is a plus aq squared plus up until aq to the n minus to the aq to the k minus 1, sorry. But then since we are talking about the case of n equals to k, we'll have to add up aq to the k, because the next term, like the k plus 1, sorry, for the k plus 1 term, since like this is the kth term, for the k plus 1 term, this is what we'll have. So if we sum the case of n equals to 1 to k, we'll get this series. But if we sum from n equals to 1 to k plus 1, this is what we arrive at. But the problem is that we don't know the sum of this series. But what we know is that this statement, this part alone, just this part alone, is equals to a 1 minus q to the k, all divided by 1 minus q. Then we add with aq to the k. We add it with aq to the k. That is what we know. We know that the sum of this alone, the sum of this part alone, is equals to a multiplied by 1 minus q to the k, or divided by 1 minus q, plus. Now this last part that we are adding is what we brought up here. Now, how do we deal with this now? This is what we'll do. We'll remember we're adding that 1 plus aq squared plus up until aq to the k minus 1 plus aq to the k is equals to a 1 minus q to the k, all divided by 1 minus q. This is plus aq to the k power. So that would be, let's add everything together. That would be a 1 minus a q to the k, then we plus aq to the k 1 minus q. That is how we add these two fractions together. Then we have 1 minus q here above. So this is a minus aq when we to the k when we set to expand, plus aq to the k minus aq to the k minus 1. Notice that these two terms cancel out. So all divided by 1 minus q. What we'll be having here is a minus aq to the, this is k plus 1 actually, because k plus 1 is k plus 1. So aq to the k plus 1 all over 1 minus q. So this equals a 1 minus q to the k plus 1 and 1 minus q. So this formula, how does it look like? We are told that the sum of the k term, that the sum of the n term, let me divide this place, because, oops, let me create a line here. And let me deal with black color. So we are told that the sum of the k term, s sub n, let's say sum of n sub n is 1 plus, a plus aq plus aq squared plus aq to the n minus 1 is which is equals to a 1 minus q to the n all over 1 minus q. But then we now prove that the sum of the n plus 1 term should also, if this is the case, if this is true, then this means that the sum of the n plus 1 term should be equal to a 1 minus q to the n plus 1 all divided by 1 minus q. So actually, these are exactly the same formula. So that means that the formula for the sum of the series here has been established. And our induction argument to prove is that since we have established for the base case n equals to 1 and n equals to 2 is true, we say that if it is true for k, then it means that it is true for k plus 1. So in this case, since you have established this result, it means that this is true for all values of n. If it that means you say, okay, what about n equals to 9? How can I say it's true for 9? Well, if it that it's not true for 9, is it true for n equals to 1? Yes. Is it true for n equals to 2? Yes. Now, is it true for n equals to 3? That is what the question is. Well, we have already proved that if it is true for 2, it should be true for 3. Therefore, it is true for n equals to 3. And we'll give it a thumbs up check there. Now, what about the case of n equals to 4? Is it true for n equals to 4? Well, we already said that since it's true for n equals to 3, it should be true for n equals to 4. So it is true for n equals to 4. In this case, it is true for n equals to 5, and it is true for all values of n. And the result has been proven to be true. And that is this induction step. So thank you for watching, and do have a nice day. Bye.